Okay, so let us start with the second speaker of this workshop, which is Marc Quincampoix from Université de Brest. So this morning we had an introduction to approachability and link to regret, and today, this afternoon, we have link between approachability and differential game. So you have two sessions, 45 minutes.
Okay, so thank you, Xavier, and thanks the organizer for inviting me in Paris, even in video. So I'm not so much expert like Vianney was to present. I will use a more traditional presentation with slides. And because Vianney has already made a very good introduction of approachability, I will not give a lot of references he has given this morning. So my main subject is approachability and differential games. I'm more a differential game specialist than a discrete game specialist. And I will explain you how differential game can be related and it can be used to prove results in approachability.
Sorry, Marc, the sound quality is not that great. I don't know if it's me or for everyone.
Yes, and I will try to be closer to everyone. Okay, and I will also explain, it's good, it's better now? Yes. So I will also explain how some approachability property can be well studied using a generalization of game in the Wasserstein space of probability motion. So let's do the framework of the repeated game model. So I consider two finite action sets. I will denote by the same letter the set and the number of elements in the set, I and G. A vectorial payoff, which associates to every pair of action IG a cost, O of IG. So because which is a vectorial payoff, it's important, an element of RK. And so I have a natural way, a matrix game, which is only a matrix with coefficients or vector in Fk, and which are in the column or indices action of the first player and the line of the action of the first player and the column of the second player. I do not, for all the presentation, delta I, the simplex, which is a set of probability on the finite set I by U, and V is the simplex delta G. So the function rho can be extended in a natural way from IG to U times V by a bilinear way. So, sorry, rho of UV is nothing else than the expectation with the probability measure, which is the product measure on U and V of rho, as it is written here. So at the stage n, players choose simultaneously two actions, IN and GN, and this gives a cost, ON, which is rho of IN GN. And I'm interested in the average payoff over the first n stage of the game that I denote by rho n bar, which is the Cicero mean of the instantaneous cost ON, as it is like this. So it's important that in the first step, I will consider a full monitoring. So both players observe the action played by the opponents at the stage n before moving to the next stage. So this is the model of the game. What is the strategy of the game? A strategy of the game for the first player, it is a map sigma, which from the set of histories, in fact, the union of n, I, times G power N to capital U. Capital U is a simplex done by I. And at stage N, given the history, so it means all the past action until the stage N minus 1, player 1 choose an action in I according to the probability distribution, which is an element of the simplex U. Similarly, tau is a strategy for the second player. And so the aim of the player 1 in the approachability is that the average payoff, ON, O bar N, O bar is always denoting a César mean, approach a given closed set E in the space of the payoff in R. Okay? So this is the first model. It was stated by Vianney this morning. So, I will a little generalize this game. This game, the previous game was there is mixed action. I will generalize it, considering the game where the player choose simultaneously two mixed actions, UN and VN, these are simplex U and V, and this generates a vectorial payoff ON as previous. So the strategy of the player 1, it is a little the same as previously. So it is the history, it's now the union of N of U times V power N. Previously it was the union of N of I times G power N. And it's associated to an history Hn minus 1, an action which is in the simplex U, and I denote it like this. So it is a little generalization of the first model because we have mixed actions. And the aim of the player is the same, the payoff, the César payoff must approach a given closed set E in A. So now I will define the approachability. It is due to Blackwell. So a closed set, in fact, there is two notions of approachability. Vianney has defined one, and also he has defined, I think, only for a convex set. I will define it for an arbitrary closed set in Rk. So a closed set E in Rk is approachable by the player 1 if for every epsilon there is this strategy of player 1 which is good, which allows the average payoff to be close enough to the given set E. Close enough, it means close enough in expectation, and D is the distance between the average payoff O n bar and the set E. So it's a distance between a point, a vector, and a set. And in all my talk, all the distance associated with this are Euclidean distance. So we have a set is approachable. It's a uniform property. It means that for every epsilon, that there is a strategy which is good for every action of the second player and for every n large enough. We have the precise definition. It could have, we can define also a notion which is an asymptotic notion. It means that the strategy, the strategy which tries to make the state near the given set depends on N. More formally, it is like this. E, a set, a closed set, is weakly approachable if and only if, for every epsilon, there exists an n large enough, such that for every n greater than n, there exists a strategy, and you know, I insist, this strategy depends on n, the number of the steps of the game, such that for every strategy of the second player, the distance between the average player and E is smaller than x. So you may immediately see with these two definitions that when a set is approachable, it is also weakly approachable. But the converse, of course, is false. And so this is an asymptotic property. Okay, I forget to define the dual notion of approachability. It is written here. A set is excludable if and only if the complement of an eta, there exists eta, so the complement of the eta neighborhood of E is approachable for the player 2. And the same for weakly excludable. E is weakly excludable if player 2 can weakly approach the complement of E eta with eta small e. So we have two notions, and I will explain later on how these two notions can be studied by differential games. Okay, maybe I have also already said something. So we have that a set is approachable, but it implies that it is weakly approachable. That you have a uniform property, which is approachability. It means the strategy is good for every n large enough. And we have an asymptotic property, which is that for every n, we can find a strategy which is good for approaching the average payoff of the target E. Okay. So we have these two notions, and now I will, and these two notions are defined with approachability with full monitoring. Full monitoring, it means that the two players observe the action of the other player. I will generalize it a little by defining the approachability with partial monitoring. So the game of with partial monitoring I will consider is in a special form. So we have, it's described by a message. It is a map from the action G of the second player to RD. RD is some finite dimensional space, which could be extended linearly to V, of course. And at every stage N, the players, when choose UN and VN, so we have still the same ideas, the payoff is still the same, but the difference is in the strategy. This payoff is not observed by the player 1. He only receives a signal, which is a function S of Vn of the action of the second player. And so the function, the signal S of Vn belongs to the image of the set of the map S previously defined. I denote calligraphical S, the image, the range of the small of this function small s. So you know that it is and we assume that the player to observe UN. So it is a partial monitoring of a special structure form. It is not symmetric, and I will consider this later. And so the strategy, the difference is now, is a mapping of the set of finite history, but finite history is not no more the union of U times V power N, but it is the union of U times S, the range of the signal into U, there is a mistake here, it should be U, while the strategy of the second player is the same as previously because he observed everything. And so with this concept of strategy, we can define in a very similar way two notions of approachability and weak approachability of a set. So the goal, as I said, is the relation of differential games and this approachability. And I will explain also that how full partial monitoring approachability will be related with a game on probability measures. And so this is the contents of the lecture. First, I will explain some already known things on approachability and we'll try to motivate the introduction of differential game. After, I will describe shortly some result of approachability and relation with qualitative differential game. And after, I will define quantitative zero-sum differential game, and I explain how this notion is used to study weak approachability. And after, I will use the same scheme to consider partial monitoring approachability using a differential game in a Wasserstein space. Okay. So the first part of the talk will concern full monitoring case. So once again, Vianney has defined it this morning. Blackwell has defined what is a B set, a closed set E in the space of Rk is a B set, if and only if and only if, it exists some P for every Z. Maybe I can show a picture. I have tried to make a picture. So for every Z, my picture is here. We have the set E. For every Z which is not in E, you can find a projection. There exists a projection P. Of course, because this set is not convex, there is not uniqueness of projection. So we have to define projection, the set of projection of Z in E. It is a set of P which realize the minimum of the distance. So there exists a P and a mixed action and a set a U such that the hyperplane through P orthogonal to Z minus P, that I have drawn in blue, separates Z from the set of payment UAV. UA capital V is a set of all UA small v when we describe capital V that I have drawn here. So it is a very geometrical notion. And once again, you have this can be analytically expressed by the fact that there exists a U such that the scalar product between rho of UV minus P scalar Z minus P is negative for every V in capital V. Okay, so we have this geometrical property and okay, and so it is easy. It's not easy. It's a result of Blackwell saying that every B set is approachable, exactly with the strategy U hat of Z that I have defined here. And from this, because when a set is approachable, every superset is also approachable. So every set containing a base B set is approachable. Okay, we can also give a notion of characterize this geometrical property. Before it was for every Z which are not in the set E. We can characterize it from inside using proximal normals. Let me show again the picture. Proximal normals. Okay. What is a proximal normal to an element X of a set E? It is all the vector P such that X belongs to the projection of X plus P to E. And so we can equivalently characterize B set by this property. What it means for every Z which is in E, in fact it has a meaning only in the boundary of Z, every proximal normals. So I have draw a picture with a corner, so there is many proximal normals. So pink one and the blue one. And so there exists some U such that for every V, we have the scalar product between P and the payoff O of V minus Z is negative. Okay? And you see, because this is, of course, linear in U and V, the min max is equal to the max min, of course. Here. Okay, so we have inside, and there is a result of Blackwell, but I recall that when we have a closed convex set, the previous condition is approachability. A closed convex set is approachable if and only if for every V in V, there exists a U such that rho of UV is included in C. Okay. Diane has spoken about this condition. And now let's try to motivate the introduction of differential games. So when we have the average payoff, the Césaro payoff, we can have a continuous analog of this payoff, which is nothing else but the integral of between 0 of t, 1 over t, of u of s, a, v of s, ds. And when we differentiate this expression, we obtain this differential equation, because it is routine to show that the derivative of gamma is equal to this quotient minus gamma plus u and v divided by t. And by making a change of variable, easy change of variable, and easy change of unknown function, we obtain this differential equation, x prime of s equal minus x of s, u of s, a v s. And this is exactly the dynamic of the differential game that I will describe now. And this is exactly the motivation of the introduction of the differential game. More generally, instead to have this specific form of the dynamic, I will introduce a larger form, more general form, which is we consider a differential equation parameterized by u and v, okay, and the state variable is x. There is some assumption saying on the dynamic f, so f is Lipschitz continuous, and u and v are convex compact. We can make more general assumptions. So we have a dynamic and an initial condition. Now, what are the set of control associate the set of function u and v? So the set of function u and v are just u of t0. The calligraphical u is a set of all measurable functions from t0 plus infinity to capital U. And calligraphical v is the same measurable function taking value in capital V, which is a simplex delta G. And I note the unique trajectory. With this assumption, there is a unique trajectory as soon as the two measurable control u and v are given. There is a unique trajectory that I define like this. You see, it depends on t, on the initial condition, and on the two controls. Now, what are the strategies for games, for differential games? It's more, it's less obvious, but for discrete game, what is a non-anticipative strategy with delay for this differential game? So it's a way to associate an action of the player one, it associate to an action of the player one, an action of the player two. So alpha, okay, I make a mistake, it should be alpha from V to U. So the strategy is a map alpha from V to U, such that there exists a subdivision of the time interval, a finite subdivision, such that if V1 and V2 are equal on S0 tk, then alpha V1 and alpha V2 are not only equal on the same time interval, but they are equal on S0 tk plus 1. So there is a kind of delay. So you know, mathematically, it's a way of mathematically express, but it depends only on the past, of course, because if V1 and V2 has the same past, the action will be the same. This is non-anticipative the way to express that it depends only on the past, and the delay says that it's the answer of the action of the first player, not only on the time interval S0 decay, but a little more. The next it's also equal on the next interval of the subdivision. Okay, I denote by R the set of non-anticipative strategy for the first player, beta for the second player. Okay, now I have defined it only for capital T finite. If type capital T is infinite, I can define the same way, but we have the subdivision could be infinite. And if it is infinite, then we have the limit of En of Tn should be infinite. And so when we have a pair of non-anticipative strategy with delay, it's very easy to show that there exists a unique control which represents this pair of non-anticipative strategy. What it means? It means that alpha of V is equal to U, mistake, and beta of U is equal to V. The proof of this theorem is easy because you see when you have a map alpha on the first time interval, on the time interval 0 T1, it's depend on nothing because it depends of the past interval, which is nothing. So step by step, you construct the map U and V, satisfying this, representing the strategy as it is. So we can make the game, any game, in normal form. Okay, and so we have to any pair of strategy, we associate a trajectory, which is nothing else but the trajectory associate to the pair of control, which uniquely represent the strategies. Okay, we have a little with Vianney some years ago extended this concept of strategy by a concept of non-anticipative strategy with delay and piecewise constant. So let me explain it. So we have alpha is a non-anticipative strategy of this class. If, again, there exists a subdivision of the time n, all the interval of the subdivision has the same length, which is t divided by n. And the second property does not change. It is non-anticipative strategy with delay. But the first property says that it's in every time interval of the subdivision, alpha of V, it's a constant quantity. Okay? So you can imagine, I will make it more precisely later on, but this is very well adapted for making relation with discrete game case. Okay, we have this concept of strategy. Okay, and when t is equal to infinity, all the intervals should have the same length. Okay, so we have a strategy of this form which will be well adapted to study weak approachability. Okay, and this is exactly this lemma. When we have a strategy non-anticipative with delay and piecewise constant, I do not abbreviate by NADC, which delay is 1 by n, that it's naturally induced strategy in the n stage repeated discrete game. It induces a strategy such that the difference between the average payoff of the discrete strategy and the cost of the differential game could be estimated by this. Okay? And for x0, small enough. I will not prove this theorem, but we have a way to associate to a non-anticipative strategy, a strategy in the discrete game. Okay. Okay, so I recall this, I can skip it. And now in the qualitative differential game, let me go back to differential game. A qualitative differential game, we have a set in the space of the state variable space where lives the variable x. And the goal of the first player is to make the state x remaining in the given set E. In fact, for every x0 in E, for every epsilon positive, which is technical, the player wants to find a strategy such that the state remain in E, whatever is the strategy of the second player. Remains in E, in the epsilon neighborhood of E for every T. And there is a theorem of Cardalia-Gay, which is in fact extension of variability theory, saying that this blue property is equivalent to the geometrical condition. This is the following theorem. So the blue property that I have to call it shortly is equivalent to the equation 2. It means that for every x in E, for every proximal normal initiated x, we have that there exists some v such that for every u, no, there exists some u such that for every v, f of x uv, scalar p is less or equal to 0. Okay. In the previous game, it is bilinear, so the max-min commute. In general, we have, in the general form, we have this theorem. And when a set E satisfies the second line geometrical condition, it is called a discriminative domain. So now remember that we are interested in a very simple game, which dynamic is more simple than the general one. It is bilinear. What means this condition? This condition with proximal normal for the specific f previously defined. It means exactly that this condition. And you recognize here it is the same condition than to say that E is a B set. So when E is a B set, E is a B set for the discrete game, if and only if it is a B set, it is a discriminative domain for the differential game because the geometrical condition characterizing these two properties on the set. Okay, and so this is why this differential game is again very natural. And also there is a very one thing for differential games, because the dynamic is a very specific form, then we can by compute and we can make estimation of the dynamic. So I will skip this. Okay, so I will prove a result already known. I think it's due first by Spinat. A closed set E is approachable if it, and only if it contains a B set. So one sense is clear, and I will explain how differential game can be used to prove the converse implication. So let's consider K a B set containing E. And I consider the Blackwell approachability strategy for the B set, K. So as it's naturally generate a non-anticipative strategy, this piecewise continuous, with subdivision, the subdivision of R plus is only in the integer, which drives a point Y0 near K for every B. Okay? And now I consider we have exactly this, and I associate to this non-anticipative strategy a discrete time strategy as defined at the lemma, which approximates the average cost of the differential game. And so we have this relation from the continuous dynamic would be translated in this relation, the distance between the average players in E with the continuous discrete dynamic. So we have again reproved the spinat result using differential game. So once again, the approachability, the non-anticipative strategy, we approach it by continuous one using this length. Okay. And now maybe I will, again, 5 minutes. Okay. So, so we have proved a not already known result now. Okay. Now I will turn to weak approachability. So I recall the definition, and you know I will explain how to prove a result obtained by Vieille using differential game. In fact, in the original paper of Nicolas Vieille, he has already used differential game, but not exactly the same that I want to discuss now. So the theorem I will consider is a closed set is either weakly approachable or weakly excluded. So I recall you the element I'm considering. We have the payoffs. The payoff to satisfy this recurrence formula, which is well known for discrete game. The differential game I will consider is the following. But here I prefer to consider the differential game in this form without the change of variable. So it is easy to see that the differential equation, the solution of this differential equation with initial condition is the following. And you know, it's why I consider only time S non-negative time S. S should be strictly positive. Okay. And so now I will define what is a zero-sum game. We have a dynamic, again, now it's dependent on S, so this is the only difference previously, because the dynamic depended on S, previously it was independent of S. Okay. So we have a dynamic. In the particular case, I will be interested by this is a dynamic. And we have a payoff, which is L. L is a function of Rk of X, evaluated at the final time 1. I will consider only the dynamic on the time interval A1. And this payoff, P1 wants to minimize it, while P2 wants to maximize it. And so this gives, as you know, this gives two values, the upper value, which is the in soup of the payoff according to strategy. So it is L of X as X0. So this is the initial condition, which will be X0. And alpha beta of the two strategies, one for the first player, beta of the second player, evaluated at the final time 1. And so we have two values, and as usually, the important question is to know when this value coincides. And so these two values, I will explain briefly how to prove for differential games that these two values coincide. So, okay, I have again given the definition of strategy, the same as previously, so I can avoid it with some references of strategy for differential games. So this is as previously defined. So it is non-anticipative and piecewise constant on intervals. I need some assumptions which are valid for the specific, very easy game that I will consider for treating approachability. I will consider L, the cost, is a Lipschitz continuous function. And so with this, the first result, regularity result, is that the two values previously defined are smooth enough. So it means Lipschitz with respect to the two variables. And okay, so this is a routine and very classical in game control. That satisfies, it is also classical, it satisfies dynamic programming principle. So the dynamic programming principle is to compare, let's explain it for V1 of S0, X0, to compare it when V1 of S0 plus H, it should be S0 plus H, and X evaluated as S0 plus H with a strategy alpha n. So we have a dynamic programming principle, and okay, formally, passing the two members in the same side of the equality and divided by H, it should operate, it should make appear the derivative of V1 with respect to the two variables. Okay, H tends to 0. And in fact, it is formally the case, and it is the continuous infinitesimal version of the dynamic programming principle. It's what is called the Hamilton-Jacobi-Isaac equation. V plus is a unique solution of some Hamilton-Jacobi equation. I will explain. There is a boundary condition. It means when we start at the final time, we have only the cost. And this is the Hamilton-Jacobi equation, the derivative of V with respect to the first variable. There is an Hamiltonian, and the derivative of V with respect to the second variable. And the two Hamiltonians are defined like this. H plus is the max V mu of P scalar F. P is in the same space and X. And H plus is the same interchanging the role of max and V. Okay. For our game, H plus is equal to H minus. So here in this slide, there is a result. It is summarized very briefly. Some result of Ivan Tsougani's Skandalians, which show that V plus has a unique viscosity solution of Hamilton-Jacobi equation. Viscosity solution, why? Because it's only Lipschitz, the value function, so we cannot give the derivative does not exist. So there is a specific meaning of viscosity solution that I skip. Now, using this result, in our previous case, we have seen, F is bilinear. F is bilinear with respect to U and V. So these two Hamiltonians, the min max and the max min, are the same. These two Hamiltonians coincide. So what means? It means that the two Hamilton-Jacobi are the same, because H plus is equal to H minus. Okay? And because V plus, these two Hamilton-Jacobi are the same, and they have unique solution. So V plus equal to V minus. This is exactly this. When V plus, the value does exist, V plus equal V minus, because they are the unique solution of the same Hamilton-Jacobi equation. Okay? So this is how in differential game we prove the existence of the value. And again, I insist that the assumptions are fulfilled for this classical, for this simple bilinear game, which will be suitable to treat approachability. Okay. So, okay. So the zero-sum differential game, now consider only this zero-sum differential game, but I recall the dynamic, the form of the solution. Again, you understand why S should be positive. And for this specific differential game, we have some more property. So V plus and V minus are Lipschitz of constant 2K. Ka is an upper bound of UAV when U and V describe the two simplices. Okay? V is Lipschitz with respect to the first variable, to the second variable, the Lipschitz constant are given this. And Murph, so because they are Lipschitz in every time interval A1, okay, for every A positive. So we can extend in a unique way the Lipschitz function V to the full time interval 0, 1. There is a unique extension because in the open set interval, it is Lipschitz with the same Lipschitz constant. And surprisingly, the value in 0 does not depend on the second part. Maybe I can make some comments on this, because if I consider two trajectories with the same control initiating with two different initial conditions, x0 and x0. By this formula, you just use this formula, and when you consider the two trajectories and you make the difference, this term disappears, and you have only this term S0 times x0 minus x prime 0. So we have this estimate. Okay? And this is valid for every S0, and when S0 goes to 0, okay. And so it's not difficult to prove that the value function satisfies the same estimation. It's not the same constant, but S0 time a constant. And when S0 goes to 0, you observe that V of S0, F of V of 0 x0 equal V of 0 x prime 0. Okay? So we have that the value does not depend at 0, does not depend on x. I have 2 minutes more. And the final result is the result of VA, moved in a different way. So if V0, if the value, we consider L the distance to K, to E. Okay? We have the set E. What I'm interested in is be approachable or not, weak, approachable or not. I consider L, the cost, is a distance to E. So the value is positive or 0. So the theorem is the following in blue. Either the value is 0, either it is positive. It's clear because it's positive or equal to 0. When V equals 0, it is weakly approachable for the player 1. When V of 0 is strictly positive, it is excludable, weakly excludable. And the proof is just to considering a strategy of differential game, which makes the value, the cost approximatively equal to 0. So, and to consider a strategy of the discrete game associated with strategy of the differential game as in the previous year. So this is the end of the first part of the talk. One comment that in the original work of Nicolas Vieille, he does not use this differential game, exactly the same differential game, but we will use it because this game could be easily extended in the case of partial monitoring when the original game of Nicolas cannot be extended to the case of partial monitoring. Sorry to have been a little long. Is there some question? Maybe I can show the question. See the question.
Okay, but thanks, Marc, for this first part in the general cover of many results of differential game. Are there questions?
Maybe a short question. Hi, Marc. Jérôme.
Oui.
So in the case of signals, you always assume that player 2 observes everything. Okay.
Yes.
So you may consider a model where also player 2 has some signal.
Of course.
Is it known in this setup which set can be approachable by player 1, given the both signaling functions?
Yeah, this is one of my open problems.
Okay.
No, in fact, there is some small things that can be generalized. Of course, when it's completely symmetric, it could be. But I prefer, the model is more easy to be explained in this case.
Okay, thanks.
Okay, so let's just take a small break and then we start again in 15 minutes, so at 3:05.
The second part of my talk will concern again differential game and approachability, and but more specifically approachability with partial monitoring. And the key point is that approachability with partial monitoring is could be equivalently studied by approachability in the set of probability measures. And it could be a paradox to study in the approachability in the set of probability measure through differential games. So it means that we have to define a differential games in the set of probability measure. But as you know, probability measure is not a normed space. So, and it should be very strange to define a differential equation on the set of in a non-normed space. Okay, so so I have recalled the definition of approachability, weak and strong approachability. This was done during the first part of the lecture. Now, the structure of signal, again, I repeat that there is a message. The first player does not observe the action of the second player. He observes only a signal. It means a map which depend on from G to RD, which could be extended to V. It is a simplex associated to G. So this is exactly the same definition in my slide before. I prefer to comment it in more, maybe an example. So let's consider an example of games with partial monitoring. So we have two players. The first player could, and you have a matrix. Okay, 2 actions for the first player, 3 actions for the second player. This is a matrix of the vectorial payoff. And the second player receives a signal which is defined on the second matrix. Okay? So you see that E and G, this, and the signal E and G are defined like this. And the signal, there is only two numbers, only A and B. So if A receives the signal A, he only knows, in fact, you see, he only knows that the second player has not played right. He has no information about if the second player has played center or left. Okay? And this is a kind of game I will consider now. Okay. So now some definition. We will introduce a multi-valued mapping, which is a map from U, again, mistake, U, the simplex of the first player action, times S, all the value of the signal map S, to RK. Okay? What is this mapping P? Is when you have an element mu in S and U in U, it is all the set of payment generated by all the action U and V for all V, for V, such that for all V, such that S of V is compatible to the sigma. So it means that S of V is equal to V. So this is a set-valued map. So the closed set E is approachable by player 1 if and only if he has a strategy such that the sequence of average of this map converge to E. What it means, when I consider, it means that the distance between the average of this, the action of Pn and E tends to 0. What is exactly this set? Pn, it is a Cesaro mean. So it means that there is action of the two players during n step. Okay? So it is the action of the players between the n step. And so I consider it is the distance, it is a supremum of the distance between Z and E when Z describe this belong to Pn bar and Pn bar. So it means, so this is a definition of Pn bar, Cesaro mean, is the sum of Zm n divided by m, and all the Z, Z1 belong to P1, Z2 belong to P2, etc., Zm belong to P2. So the partial mean monitoring somehow say that this map tends to 0. And there is a result, also, I recall the result that a closed convex set is approachable with partial monitoring if and only if this map that I have defined, that for every signal mu, there exists an action mu, so that this map is included in C, the closed set C. So this generalized the Blackwell result for full approachability. I think in Kohlberg it was okay. I will not comment. So I recall this. So now I will try to consider approachability in this context. First, I will transform the problem in a more abstract way. Let's explain how. So I will identify first the action UV, which are action in UV, with a product of two Dirac measures in delta U and delta V. So you see, you make an abstraction. U is a simplex of action I, and so you consider the probability measure on the simplex E. So it is delta of U. It's delta of delta of. So clearly, when you have 2 points in UV, it is identified as the product of two measures which are Dirac mass. Okay. So I denote by a bar. I have two measures X, Y. X, Y of the action. I will denote the average of the Dirac mass. So X is a sequence of action, X1, X2, Xn. Okay? Okay, so now consider the full monitoring case. It is the consideration in blue. Somehow, in the full monitoring case, you want that the average payoff belong to E or E plus epsilon. So let's consider E. There exists a strategy such that for all strategy of the second player and for every N, etc. So I will just transform this equation, this average payoff belong to E. So this is the first relation is just that the average payoff, it is a definition, the average payoff is a Cesaro mean. Of course, this second relation could be just written as an expectation. This quantity could be considered as an expectation of O with the Dirac product of Dirac mass, UM, VM. Okay? And with my notation here, I can consider just this as an expectation of rho with respect to the U times Vn, this notation. Once again, I can say that it is the same to say that this probability measure belongs to a set E tilde that I define now. It is a set of probability measure on U times V such that the expectation of rho with respect to Q belongs to V. Okay? So in fact, this blue line is just the full monitoring approachability. It's just a translation. It should be a little surprising and not interesting. In fact, it is not very interesting in this case. But we just have transformed the property in a bigger space, the probability delta U times delta V. For the partial monitoring, you have seen that it is to check if this map belongs to a neighborhood of E. So this map is included in E. This is just the translation of what is PM bar. Okay? And again, this is nothing else than the expectation of the set valued map P is included in E. There is just small things. P is a set valued map. What is an expectation of the set valued map? So it is the Oman integral of set valued map. So it means it is a set of all expectation of all measurable selection. Okay. And so this is equal again with my notation, saying that the expectation with respect to U times mu of P is equal to E. And so again, U, the bar of U times mu n is included in the set E tilde, which is defined in a very similar way as previously, but here we have expectation of P is included. Should be included. Okay, so you see these two obvious remarks, in fact, say that the two properties are the same if we consider these two properties on an abstract space, which is the probability measure of U and V. Okay. Okay, and in both cases, we need to, so I have repeat the same consideration. In the both cases, we need to check if an average of a map belongs to, of a map capital P, belong to a subset of E, a neighborhood. For the full monitoring case, capital T is a set-valued map. It is just the singleton row, and Z is equal to V. And in the partial monitoring case, P is exactly the map, capital P is a map K, and Z is equal to S. So the two properties are the same. And in fact, we can define it for more general P, not only these two one, but I will skip this. So now I will define again in the space delta U times delta V. Okay. So we consider two compact and convex subsets U and Z on some Euclidean space, and I will define the following game that we call purely informative game. A player 1 and player 2 choose at the stage n, respectively an action un in delta of u and yn in delta of z. So what is the outcome? The outcome is a probability measure. It's very theta n, theta of u and n, which is nothing else than the product of the two probability measure un and zn. So an element, it's a probability measure on u times z. And what is in this game an action of the first player, a strategy of the first player? It's a measurable mapping from the past history of action of this game, from this set, to delta U. Yes. See, this is for the first player, and for the second player, it is a map sigma from delta u times delta v to delta v. And so with this kind of strategy, as soon as that we have a pair of strategy, we have a unique sequence u and zn, and so we have a payoff and an average payoff. So this is a pure informative games we consider. I think sometimes I think Jérôme Bonneau has defined it as a super game. I'm not sure. So now we will consider approachability in this game that I gammatic. So a closed set of E tilde, delta u times delta z, is approachable by player one, and we have exactly the same definition. For every epsilon, there exists a strategy of player one, such that for n large enough, and every strategy of second player, the distance between the set E tilde and the average payoff theta n is small. So we have here the distance between E tilde, which is a set of measure, and theta n, which is an element of the set of measure. So we define as in fact, it is a Wasserstein distance. It is a distance between on the set of measure. Okay, so we have a distance between a measure and a set of measure. It is an infimum between the distance of the measure and theta for every theta belongs to each theta. Okay, I will define later on what is the distance W2 very precise. And so it is the same idea. And now let's give two notation. Let's consider E a subset of Rk and E tilde a set of delta uz. What is P minus 1 of E? P minus 1 of E is a way to associate measure compatible with the E. It is a set of measure of all, it is a set of all theta measure of delta u times z, such that the expectation of P is including E. So it is a subset of delta u times z. Conversely, if I have E tilde a set of probability measure, I can define P of E tilde, the set of X in Rk, such that X belongs to the expectation of the map P for every theta, when theta describes E tilde. So we have this map can associate to a set of in Rk, a set in the probability measure delta u times z and convex. And now we have this elegant property. It is that a set in Rk is approachable in gamma if and only if P minus 1 is in delta, is approachable in the game gamma delta. Okay, so we have equivalence between approachability in E, in gamma, in the original game, and approachability in the new game through this map P. Conversely, if a set is approachable in this generalized game, in E tilde is approachable in the generalized game, then the set P of E tilde, which is a subset in Rk, as it is defined here, is approachable in gamma. Okay. And okay, we have also that when we have convex set in Rk, P minus 1 of C is a convex set of probability measure, and for C tilde, a convex set of measure, P of C tilde is a convex set. So you see, now to study approachability with full monitoring, it is exactly the same to study approachability in this for this abstract game with through the map capital P. So this is in fact we have done it in a paper with GAMENET. Okay, so maybe now I need to define what is Wasserstein distance, and I don't want to be too much technical, so I have only 2 slides on Wasserstein distance. So I do it with very different notation on purpose because I will apply Wasserstein distance in different contexts. So let's consider mu and nu, 2 measures in this set, delta 2 of Rn, which is a set of probability measure with finite second moments. So the square Wasserstein distance between mu and nu, so there is a square, and space. W2 is the square root of the infimum of this integral. So you integrate gamma of x, y, you integrate the square x minus y, the Euclidean norm of square. The infimum taken over the set P mu nu. What is P mu nu? It is a set of probability measure which first margin on the product space, which first margin in nu and the second margin in nu. So you see, this is in fact a convex capital P of mu is a convex set. Easy to see. It is compact, in fact, when we consider the topology associated to the weak star convergence of measure. And you have the minimum of a convex compact set of a map of a function of gamma, which is linear. So there is the infimum is attained, and we call an optimal plan every gamma which achieves this limit. And we have a linear problem, linear optimization problem. So there is a dual problem. This is a theory of the dual problem. It is also the same quantity. It is a supremum of some g of phi and t. Phi and t are 2 functions, and it is linear with respect to phi and t. It is a set of integral of phi with respect to nu plus the integral of phi star with respect to nu. And what is, we take the supremum of the pair phi star. So phi star first is the conjugate of phi with this formula, conjugate of phi. Xi is a set of pair phi star, phi conjugate, phi and its conjugate, which are L1, which is integral with respect to u times integral with respect to u. And so this supremum is attained by also attaining when this supremum is attained, we call it a Kantorovich potential phi. So Eitan, it's again a potential, but this is untransported. So this is only 2 slides that I need to consider, 2 slides of basic fact of optimal transport. So now I can define in this abstract game gamma tilde what is the best.
Maybe one question, Marc, if I may.
Yes.
So you use Wasserstein W2, but if you take any other WP or any metric compatible with the weak star convergence, it will not change the fact that the set is approachable or not, no? Or will it change?
It does not change, but you know, in the classical case, the Blackwell condition is expressed with a scalar product. To be a base set, to check condition with a scalar product. Okay.
Yes,
so,
but because
so I will need an equivalent of scalar product in the Wasserstein space. And to have a good scalar product in Wasserstein space, it's good to consider W2.
Okay, I understand, but this is for the proof. But for the statement, if in the definition I change W2 by W1, the theorem is exactly the same, no?
Yes, but there is, yes, exactly.
Thanks.
The previous theorem was the same. Now, to call B set, yes, in fact, this could be exactly the same.
Okay.
This blue proposition, the only result that I have for the moment. But now, to work on this, we will need Wasserstein distance W2. And B set, what is a B set? B tilde set, the set E tilde is a B tilde set for this generalized game. If and only if, for every theta which is not in the set, there exists theta in the projection, such that for when phi is in the set Xi between theta and theta bar, in fact, it should be phi star, so phi is the first element. There exists some u, an action which depends on theta, such that, and this plays a role of the scalar product in B set. So you take the integral of u times z with respect of phi, with respect to which measure? The measure theta bar, theta underscore, là, theta underscore, minus u, minus the product of the measure u and z, less or equal to z, to 0 for everything. So to define this notion of B set, it's important to consider this is an equivalent of the proof of the Wasserstein of the usual B set. Okay?
Marc,
and we
in the first part, you presented an internal condition for B set. Can you have the same?
Yes, this is my next slide. This is an external condition, okay? And of course, we have proved that a set E tilde is approachable if and only if it contains a B tilde set. So this is a result, an extension of the skinat result in the case of pure of partial information, partial monitoring, sorry. And the answer of what Xavier asked is the inside condition. So we have to define what is a proximal normal. And for defining a proximal normal, it's absolutely necessary to consider it in W2. So a measure is in the project, let's give some definition. A measure mu bar is a projection of mu if it's realized the minimum of the distance. Okay? It's a projection of mu on A. If it realizes the minimum of the distance. And what is a proximal normal? So a continuous function will be a proximal normal to A at mu bar if it is a Kantorovich potential from mu bar to some mu So which projection is mu bar? So you have exactly the same definition of proximal normal. And now again, Jerome, it's very important that it is W. So we have this notation for the set of proximal normal. So in fact, of course, we have a measure, the proximal normal in the dual set, so it is a set of functions. And a set, the inside condition that Xavier wishes is E tilde is a B tilde set, if and only if, for every theta in E tilde, for every proximal normal at theta to the set E tilde at theta, there exists some action u. For every z, we have this condition. So this answers your question. So we have the equivalence inside and the condition of a B tilde set. Okay. And again, we have the theorem that a closed and convex set C tilde is approachable if and only if, when it's closed and convex, we can define it more in a shorter way. For every Z, we can have a more simple formulation. For every Z, there exists U, so that U product Z in CT. So this is a Blackwell result again. And we can also have that every convex set is either approachable by player 1 or excludable by player 2. This generalized the approachability. Yes, but you know what is not clear in the Wasserstein space? We have considered the average of this probability, the Cesaro average of this probability things. But in fact, there is many notion of convexity in the Wasserstein space. So we can, instead of having the Cesaro mean with this concept of convexity, we can have an average with different concept of convexity. So I can I skip. And so now I define it, the differential game in Wasserstein space. Okay, so I will not define the game exactly in delta U and delta Z, but I will define it on subset of delta U and delta Z. So it is a subset delta in this small delta, where delta is positive, is subset of delta U and delta Z, which such that these are convex and compact sets, and it is formed by a probability measure which has density, and density bounded, lower bounded from 0 by delta. And it is known that every density delta could be approached, delta approached by a probability could be approached by a density, probability measure in the set. Okay, and we denote delta of U, Z, the convex hull of the measure of the product measure U and U when you describe delta, delta and V delta. Okay, why we consider this? We consider this because we want to have uniqueness of the Kantorovich potential. This is a little technical. And now the differential game that I consider is the following. So the action, the control measurable map from S01 to D delta of U, delta of Z. Okay. Non-anticipative strategy, piecewise constant, exactly the same definition that between the sets. Okay. Now the dynamic. So the dynamic, I cannot define, I define the game, you remember? The game, I will not define a differential equation, but I will define the dynamic as a solution of the linear differential equation I was interested by in the classical case. So it is a dynamic, it's written in the integral form, theta of S, it equals S0 divided by S, theta 0, plus 1 over S, this integral of probability measure and initial condition. And of course, this has a meaning in the space of probability measure, because you just make an average of probability measure. You have not a differential equation, but you have an integral form of the differential equation, which is valid for this case. And we have the terminal payoff. The terminal payoff is nothing else than the theta evaluated at the terminal time 1, the distance between the theta evaluated at the terminal time 1 and E tilde. And this is the Wasserstein distance. So we have two values. So I can be a little quick. These two values defined like this. These two values are Lipschitz continuous. And remember, in the first talk, part of my talk, I have explained that these two values are equal because they are the unique solution of the same Hamilton-Jacobi equation. what is the Hamilton-Jacobi equation in the Wasserstein space. And okay, now I have to be very quick. So I did work on this subject on many, since several years. So first there is a dynamic programming principle, and it's possible to state a dynamic an Hamilton-Jacobi equation by passing to the limits. So just to have an idea, when you have a measure theta at the map phi in L2 of theta, you can define this Hamiltonian, so in sup of this quantity, which is linear. So it is a sup inf. And the Hamilton-Jacobi equation is like this, when omega, the solution of the Hamilton-Jacobi equation, is a function of t and of the measure theta. And we can define a viscosity solution of the Hamilton-Jacobi equation. Okay, to define viscosity solution, we need to define a superdifferential, and the superdifferential is defined as follows. And we define a subsolution and a supersolution with subdifferential. So the very difficult part and very technical part that we have were passing in working with GAMENET was to proving the uniqueness of solution of such Hamilton-Jacobi equation. Now we know a little more, but it is possible to prove that V plus and V minus are Lipschitz continuous and they are viscosity solution of this Hamilton-Jacobi equation. And the difficult part is to prove the uniqueness. In fact, we have obtained a comparison principle saying that if we have two functions, W1 and W2, which are respectively sub and super solution of the Hamilton-Jacobi equation, then, so imagine that they have the same boundary condition, so it means that this quantity is equal to 0, so the infimum is equal to 0, so it means that W2 is always greater than W1. And exchanging the role of W1 and omega 1 and omega 2, we have that omega 1 equal omega 2 if there is the same Hamilton-Jacobi equation. So we have proved this comparison principle, which is a very technical part of the paper. And as a consequence, because there is uniqueness, the two values coincide. Why? Because they are the same. They are both the unique solution of the same Hamilton-Jacobi equation. In fact, since the paper with GAMENET, we have made a lot of progress on Hamilton-Jacobi equation in the Wasserstein space, not for games. And it's now we do not really need this small delta. It's better to explain like this. And so now we have a generalization of VA theorem in the case of full monitoring, partial monitoring, which is the problem, which is equivalent to approachability in the abstract space, weak approachability in the abstract space. Any closed set E tilde is either weakly approachable or weakly excludable. And more precisely, it is weakly approachable if and only if the supremum of epsilon, of the limit of the value function defined previously for delta and E epsilon tilde, it's an epsilon neighborhood, is equal to 0. When this quantity is equal to 0, this is weakly approachable, else it is weakly excluded. I will not prove it. Okay? But the idea is the same. And this is a motivation why in the first paper, in the first part, when I have proved the VA theorem, which was known in the full monitoring case, I did not consider the same game that Nicolas VA did, because in fact, the same game could not be easily extended to Wasserstein space. Now, the dynamic could be extended to Wasserstein space. Okay, so we have, and so this is a new result. The previous result of the first part was not new, but this was new, in fact, at least. And so we have, as a corollary, when we have a closed set E in RD, there exists, if we have a closed set such that which is the set of expectation of the map P for all Q in some E tilde, but a closed set satisfying this is either weakly approachable or weakly excludable. Okay. And so it means, of course, that in the space, in the game E tilde, it could have that there are sets which are not neither weakly approachable, neither weakly excludable, only because when you take the inverse by the map P and P minus, it could be empty. And you can construct a lot of examples. And I think Vianney did it in a different, in a paper. Okay. And I think this is, I forget. Okay. Thank you for your attention, but I want to speak about some open problems to end. First, the open problem spoiled by Jérôme, when we have another concept of full or partial monitoring. It was a very specific case. We have only what's partial. In the presentation I give, there is only full partial monitoring from one side. What happens when there is different structure, symmetric, etc. Also, it would be interesting to study approachability with constraints. For example, in the spirit of the paper, recent paper of Elon, we can consider all this theory considering approachability with constraints. It means the payoff not only should approach a given target, but it should also remain in a given set of constraints. Okay, we can also think instead of having a finite action of player in the original game, what happens when we have a compact set of actions. Okay, we can also study this problem in Hilbert space, full of possible generalization. Okay, thank you.
Thanks, Marc. Is there more questions? Or will be being some during?
So I was just wondering, is there a proof of the Nicolas Vieille's results that does not go through for differential game? Or is it?
I don't know. The original proof of Nicolas was with differential game.
I'm just I don't think I really understand well, I mean, at which point it's what makes the argument work. But I mean, like, why couldn't you do some discretized version of this proof? But I mean,
I don't know. Maybe Laurent, maybe Sylvain, you know?
If you think of the proof using Hamilton, Jacobi, Bellman, it's an easy way to prove that lim sup and lim f of Vn are the same, and it's easier to prove in the continuous case.
Damping coefficient you are allowed to take in
Okay.
order to get a positive.
So,
and we're going to see, just like always, critical situations are often the most interesting to consider, which we're going to see that precisely the case of an
these games are very specific games, okay? It's game with complete information. There is no stochastic aspect. There is no lack of information, okay? It's just that you have vector pairs. Okay.
In the
So
case of a
the
German
dynamics
grammar,
is very simple,
so we introduce
and it's
this
very
function,
easy to mimic
depends on
the
gamma,
end stage
under
game by a
those
differential game.
conditions,
And then the
product
proof
of gamma
that lim sup and lim
and
inf coincide
capital
for
gamma
Vn is easier by using simply the Hamilton-Jacobi equation and the proof that there is a unique solution there. Basically, the comparison principle
And
there.
if you return to the critical case, gamma of t or alpha of t,
Yeah.
you are going to see that the
Okay.
coefficient here is going to play a fundamental role.
I think there is a radio or something.
Yeah, I can't.
Okay.
Okay.
Maybe I can ask another one.
Yeah.
So in the standard model in repeated games, players, they play mixed strategies, so they play probabilities, but what is observed in the standard case is the realization only. Or in the case with signal, it will be a function of the realization, not on the probability which is used. So here, if I understand well, this is not what you do. So it's not less or more general, it's a bit different. So here, for instance, it makes no sense to ask, can you approach this set almost surely?
Yeah, I understand what you said.
This morning, we had in expectation of the distance goes to 0, and also almost surely the distance of the average payoff to the set goes to 0. So is it really different? You cannot handle this case, or what do you, what is the difference?
I think once Vianney explained me that the approach could work in the two cases, but we did study the more easy case. I cannot answer. Maybe Vianney, you know?
I didn't hear the question actually.
The question is, what you do is you assume that you observe a signal of the mixed action of the other players, not of the realization of the action of the other player.
Okay.
So what is the difference?
Actually, this is just a small trick. If you, as I said before, like in Bandit, you can well, actually, it's a weaker requirement because, like, if you observe a signal of the mixed strategy, it's weaker than seeing the signal of the pure strategy.
It's not obvious at all. Here you lose some statistical aspect. For example, in stochastic game, it will be very different, no?
In stochastic game, yes, because you might be stuck. But here basically, you know, by saying, well, I'm just going to observe a signal with respect to the mixed action of my opponent, it's like I'm mixing the signal I'm receiving. So actually, I'm losing information.
But in the standard setup, for instance, you don't observe the mixed action of the other player, and sometimes you need to reconstruct it. So it's not that you lose, sometimes you also win. No? I don't think why it's more general what you do. I think it's not comparable. Maybe the same.
No, because you can always, like, if you're doing like, you know, like doing by blocks and stuff like this, it's you can go around those. I mean, I would have to look precisely, and I don't remember exactly, but you know, it's always a matter of because I was thinking about what at first I thought you were asking what your own signal, whether it depends on what your action or not, but
because here you lose some correlation, no, between your signal and your payoff by doing this.
But in fact, we can in the full monitoring case, we have exactly proved in the old paper with Silva that approach the two coincide, because in my context we have proved that we have that a set is approachable if and only if it contains a B set, and the B set is the same with the two concepts.
yeah. So I agree with Marc. I think in in this very specific case, actually, you can show, if I remember correctly, that you can show that both observations are not identical. I agree, but you can go from one to the other one without losing anything.
But it's not a direct way.
It's not obvious. Okay, yeah.
Is it written somewhere, or it's like something you know, but you know how to do, but you have never written it?
No, it's written clearly in the paper of Assolimani, Quincampoix, in the case of full approachability.
But in
full,
the case of
full
signal,
monitoring.
In the case of signal, it's written as well.
okay, where?
In the paper with, I mean, I have to. It's either in the paper of with Marc. I don't remember. It's either in the paper of Marc or like in the previous paper I had, where we managed to get the equivalence, and then with Marc we say, well, just take it as granted. Let me just look.
Okay, I believe you.
In my paper, we have just put a remark. Our common paper, we have put a remark that it is the same. If you want to have a detailed proof, you should ask in the paper, look at the paper of GAMENET and someone else.
I'm trying to see if I can see it, but yeah, it's either in this paper or in the previous one. I don't remember if we put again the IDs for this in this specific paper.
Okay, so just it is not an open question; it is known and already done.
I think it's known.
Yeah.